advanced brick detailing. So it's not about the more kind of conventional cavity wall brick detailing that you're probably familiar with from undergraduate, perhaps. It's more about larger multi-story brick construction, okay? And it's a very different type of construction. I'm going to just, what we're going to do, I'm going to use a building as a vehicle to describe it. And this is a school which I was the project architect for. And it's obviously, as you can see, it's a brick building. And it's a 3-story building. It's a steel frame building, brick cladding. And what we're going to do, we're going to look at 3 particular conditions. So we're going to look at the point where we meet the ground, down here. Okay. We're going to look at the head of a window, and we'll look at the eaves. Okay. So we're just going to tackle those 3 points. I don't think we'll have time to look at the windowsill. If we do, we'll have a go at that. We'll look at those 3 conditions, and as before, we'll use those 3 conditions to pick up some kind of important constructional and detailing themes. Okay, so let's start at the ground, and I'm just wondering if I've got any site photos. Possibly. Yeah. So that's the condition of the ground. We'll come back to that actually. We'll do some drawing and then we'll come back to that one. Okay, so let me go into start drawing. Okay. Right. So just getting that in the right place. So first thing, a brick. Okay, a UK brick, they're all the same size. Okay, just get that in your head. You can buy ones from Holland and they come in weird sizes. British bricks are that size. They don't ever change, always the same. 215 millimeters wide, 65 millimeters high, 102.5 millimeters deep. Okay, always the same. And as soon as you do start doing a building in brick, what I'd say is get a brick calculator. Just type into Google brick calculator. You'll find lots of them. You get charts, or you get sort of online calculators, and all they'll do is you can simply put in a dimension or put in a number of bricks. It will tell you the dimension. You give a dimension, it will tell you how many bricks that is. It will add up all the mortar joints. Really great tool, okay? The point is, as soon as you start designing a brick building, you have to design it in modules of bricks. Okay? Now, some people cheat, and I have come across architects who don't bother, and they let the brickies sort it out on site. And bricklayers are very skilled, and they can gradually increase the perpend widths. The perpends are the joints between the bricks. They're very skilled. They can gradually increase those, and they can get rid of mistakes in your design if you've not designed to brickwork dims. But really, I think it's just poor form as an architect. Okay. So the thing is, get your brick calculator out, and from the beginning, start designing in brick dims. So this building, we based it on a 7.2 metre frame, 7.2 metre grid. 7.2 is a brick dim. So you type that into your brick calculator, it will tell you how many bricks that is. So everything we did started on a 7.2. We therefore knew that you could divide that into bricks. Floor to floor heights, 3.6 metres. 3.6 is a multiple of 65 plus 10. So again, we knew we would always land on a brick. Really important. Now the other thing with your floor to floor heights is you need to have an equal number of risers on a stair, and that has to comply with regulations. But wonderfully, a brick plus a 10mm mortar joint is 75mm. Two of those is 150. 150mm is the standard riser for a public building now. Okay? So if you design your building in multiples of bricks, well, multiples of 2 bricks, it will work in terms of stairs for all public buildings. Okay? So that's just an important thing to start with. Where's my chocolate?
What would you like?
It's probably a bit late for that, isn't it? Just go on. As long as it's not a coffee. Not a coffee.
I'll pass it forward. Oh, yeah.
Right. So we're going to look at the ground condition. And as always, we'll start drawing something we know. I'm going to draw it 1 to 5. Let's just go up here. We know we've got bricks. Okay, so there's a brick width. Try and focus that a bit. Come on. There's a brick. It's 102mm wide and it's 65 high. So we'll just measure that one just to make sure that everything else is about right. So we know we've got some bricks. I'm just going to draw some more. I'm not too worried now about how accurately dimensioned these are, but as long as they're roughly right. So we know we've got bricks going up. And we know we want those bricks to meet the floor. Okay, so there's some bricks. Now, the next thing to understand now with most modern brickwork is we're not building the inner leaf typically in block. So when you're doing a domestic building house, you're probably quite familiar that the inner skin would be a skin of blockwork, concrete blockwork. Now, for most larger buildings, blockwork is often considered too slow to build on site. Okay, it's also quite heavy, but the main problem is it's too slow. So what we do nowadays is we build the inner skin from a light steel frame, and we clad it on the outside with what's called cementitious particulate board, or CP board. I'll pass that around, and it's just a compressed board with a lot of cement in it. So it's very robust. You can drill it. It's not affected by water particularly. So we use that on the outside, and on the inside we'll typically be using plasterboard. Right, so I'm going to draw that. Okay, so I'm going to leave a bit of a cavity. And here is our lightweight steel frame, which on this building was a 150mm section. Okay. Now, these lightweight steel frames will be designed by a specialist, so you don't need to worry too much about that. It's just lightweight bits of pressed steel, and they can screw it all together on site. I've got some pictures of that. And so we fix to that on the cavity side our CP board, which is what I've just passed around there. Okay, and that's replacing that more kind of old-fashioned blockwork inner skin. Now, there's nothing wrong with blockwork inner skins, and if you can, if your contractor is happy to use blockwork, great. It's really good and robust. Great for fixing too, but normally it's not cost effective. So there's our CP board, lightweight steel frame, and on the inside of the building we're going to fix some plasterboard. Which will typically be a sort of 15mm plasterboard like that. Okay, so there's our basic lightweight steel frame inner skin. Now that brickwork needs to hit the ground, needs to land on our foundations. And we don't want to see foundations sticking out of the floor. Okay, so you don't want to see bits of concrete around a building. So normally you'll take that brickwork into the ground. So what we do know is that the floor of our building has a concrete slab, which is this, and we will typically want our lightweight steel frame to sit on that concrete, because we need something to fix to. But if we just continued, if I draw our outside ground level as here, okay, if we just continued that concrete slab across, it's going to be sticking up out of the ground, which is not, you do see that sometimes, but it's not really very good detail. So what you typically need to do is to put a toe into your foundation edge. So I'll just draw. You notice I am cheating again. Okay, I'm not going to show you that, but I'm not just doing this from memory. Okay. So we put this toe into our foundation like this. Now bear in mind that foundation is designed by an engineer. Don't get don't be too worried about designing foundations yourself. And basically that is then just a big lump of concrete in the floor, like that. All designed by your structural engineer. You would tell the structural engineer what levels you wanted, and you would need to give the structural engineer this level, and you'd need to give the structural engineer this level. Okay? And this level here needs to be on a brick dimension, because you're going to sit your bricks onto that. So I'm just going to draw my bricks down here, and I haven't measured it, so they may well not quite land. Okay. Okay, but you get the idea. That should have been on a brick dimension, so that brick nicely landed on that. So what we've achieved now is we've got our bricks coming down to the ground. They disappear into the ground, so we're not seeing that foundation. And we've achieved that by having this little toe on our slab edge. Okay, very effective. Right. Let's talk a little bit about tanking below ground. Right. It didn't really work, did it? Don't get too confused about tanking. It's pretty simple. I'll just draw it while I'm chewing. That's where your tanking goes. Okay? Right next to the concrete. People do kind of get confused about putting it above the concrete slab, but really it's best just to put it below. And what they'll do on site, they'll dig this hole, they'll either line it with sand, which is called blinding. Okay, so they put a bit of soft sand down there, and that soft sand just protects the membrane from being punctured, because then below that you'll have some rubble, some hardcore. Or if you're insulating below the slab, this would be insulation. Okay, you often you often end up not insulating below the slab because you don't need it, because of the you've got the effect of the thermal mass of the soil. Often it's actually not that important. Sometimes you do, but not always. Okay, so that's just our sand. Now what they do with the membrane, when they get to the edge of the concrete, they'll leave a bit spare hanging out, and then they'll actually use a self-adhesive tanking membrane, and they literally stick that to the concrete. So it's like sticky back paper. So it's very, very thick, it's very, very sticky. Okay, but they literally stick that on. And where they've overlapped the membranes here, they can stick it back over the membrane that they've lapped over. And that will give you a complete intact waterproof membrane around your concrete, which is just stopping any water in the ground getting into your concrete. Okay. Now ideally you might have a specialist subcontractor doing that, and you get a guarantee with it, but not always. Okay. So there's our kind of basic principle. Now just to neaten this up, what we asked on this detail is for that membrane to just be stuck up the face of the CP board. Okay, like that. Now, we need, what's next? Yes, we need to put a cavity tray, because this is still a cavity. So although we're not using block work, it's still a cavity construction, and bricks are kind of permeable. So when it's raining out here, that brick can get damp, and that water can collect on the inner face of the brickwork and run down the inner face. Don't get confused, it doesn't fly across the cavity. Some people get all concerned about this inner skin getting wet, but it can't jump across the cavity, it can just drip down the back face. Okay? But you don't want that water dripping down the back face of your brickwork and making a pond in the bottom. So we need a cavity tray to get that out. Now let me just draw that in here. And that is just typically a thick piece of plastic. Okay, like this. And the idea there is you form that plastic tray, and any water that dribbles down the back of the brickwork will find its way out. And what you need to do is put a weep hole in here. And a weep hole, unfortunately I haven't got one, is just a little plastic insert that you put into the perp end, and it just lets the water dribble out. Okay? They look like, I'll draw one over here. They kind of look like that. So the water can get into it, dribble out, and it just drips out the front. Okay. So that's a weep hole. Now, you might notice I've put that cavity tray, I've sort of left it floating at the moment. Now that's because in this instance, what we did was we stuck that to the insulation. So our insulation came down like this. And in this instance we were using a closed cell Kingspan type insulation, and we needed about 50 millimeters of insulation. Okay. And so the cavity tray here is just stuck back to the insulation. And again, this is where people get worried, because they think water will get down the back of that, but that water can't jump across the cavity. Okay. So any water in the cavity can drain out. Now we need that insulation to continue below ground here. And also, what we need to be careful about is when we backfill, this will all be soil here. We've left an air gap here. Now if we backfilled that, there's a risk that it could squash all that brickwork, and that brickwork could collapse into that cavity. So what we would typically do is stuff that full of a very tough compressive insulation. And that insulation is called foam glass. Okay. And foam glass is a really great product. It's made from recycled glass. It has very good environmental credentials. It's impervious to water. So even if you stick it in a bucket of water, the water can't get into the air pockets. And it's got very high compressive strength. So you can actually lay bricks on it. Okay, that's foam glass. Pass that around. So what we've done, we've stuffed that cavity with foam glass there, and that means we're not worried about the cavity collapsing. And we're not worried about water getting in there and compromising our insulation, because that insulation doesn't care if it gets wet. Okay, there's a little gap here, so we put a little piece of insulation in there as well. Yeah.
How much of that insulation do you need compared to standard?
You probably, well, it's complex because you're below ground. You've got a lot of soil, so you probably don't actually need very much at all. But you normally just put enough to fill the cavity. Okay. Now, cavity width, you'd be looking for at least 100 millimeter cavity to let you get say 50 mil of insulation in and the 50 mil air gap. But on this building, that cavity dimension was determined more by the size of the steel work, because the steel work was projecting into the cavity. So we had some quite wide cavities on this building. Okay, so we're almost done for this detail, but what we haven't done yet is there's nothing tying this brickwork to anything. So if you imagine, we're going to continue that brickwork up a full story height, and that's a lot of bricks sat on top of each other with nothing holding it together. So what you would do is you would use a cavity tie. So a stainless steel tie, which you can screw back to the CP board, and about every 600 millimeters vertically, you just tie that brickwork back to your inner CP board. Just holds it in place. Okay? And that pretty much is that detail done. Okay, but what I just want to now briefly talk about is the different building layers. So the thermal layer, we've got thermal continuity through here. Now, although we've not got insulation down here, we don't need it because we're below ground in this instance. We've got thermal continuity. In terms of air tightness, what we do is we seal all the joints in the CP board. We tape them together, and that gives us a completely airtight line. Okay? So that's that detail finish. All we've not got is a floor finish, and you need a skirting board in here just to hide that join at the floor. And in this case, because it was a school, the floor finish was rubber flooring. Okay. Oops. So any questions on that before I move into the next condition? Okay. Right. Let me get my next one. I'll go back and look at some of the pictures at the end. Okay. Right. So the next detail that we look at is our window head. So again, we'll start with what we know. We know we've got bricks. Okay. So there's some bricks above our window. Okay. Now, how are we going to hold those bricks up? Because we're not, this is not a traditional load-bearing brickwork where we can use an arch or whatever. Now, you could put a concrete lintel in there, but on this building, if I just go back to my pictures, look at that one there, do. What we've opted for on this building is we've not got an expressed lintel, okay? It's just a kind of floating brickwork. And when you look at the size of the windows, you could never, well, you could, but can you imagine the size of the concrete lintel you would need to span that window? It'd be enormous, okay? So we're not doing that. This is not load-bearing brickwork. It's brickwork held back to a frame. Now, what we used was, and this is very common now, is use a stainless steel support system. Okay, and that is going to hang your brickwork. So these are obviously much longer, and they come to site to the right size. This one has to be an adjustable one, where you can undo that and take out the angle, but most of them come just welded up. Okay, and they are stainless steel, so they don't rust. They're quite expensive, but they're good products. Made in Sheffield, so Ancon and Wincrow are the main suppliers to the UK, and they're made in Sheffield. Okay, so what that will do is that will hold up our brickwork. And I'm just going to draw the detail. In fact, I'll show you. Let's just look at a picture first. Okay, so that's a good one. So if you can see there, what we've got, the white thing is that's a stainless steel bracket. We've painted it white. That's an intumescent paint to fire protect it. Okay, but normally they come stainless steel coated like that. And the brick is going to sit on it. And this is called a pistoled brick because it looks a little bit like a pistol. Not much, but a little bit. Okay? And so we're going to pistol that brick, because what we don't want to do is if we just sat a normal brick on it, then you're going to lift that brick up and you'd see the edge of the stainless steel through it. So we pistol the brick, we chop a little bit out of it. And a skilled brickie can do that on site, or sometimes they pre-make them in the factory for quality purposes. So let me just draw that detail. Right, so there's there's the pistol brick, and we're going to sit that on our stainless steel bracket, and I'm going to draw slightly different from the one I'm passing around. I'm just going to draw a welded one, okay, not that kind of adjustable one. They're less common. If you can use those, they're great because you've got more tolerance on site. With the welded ones, they need to come to site and they need to be exactly the right size. Okay. And then the nice thing about these, the really great thing about these, is the bracket can be pretty much any size and shape you want. So I'm just going to sort of make this up. I've drawn that with the wrong pen. That's in elevation. Okay, that should have been drawn with a thin pen. I'll leave it. All right. And that has a stainless steel plate along the back of it. And typically they just have a single bolt connection here. Which lets you fix it back into your steelwork. Zoom in on that a bit. So, stainless steel bracket. This is a welded connection normally, and your brick, your pistol brick, can sit on it. So we're holding up our brickwork now. Now we need to fix that bracket back to something. You can fix it into concrete, you can fix it into steel. The key thing is you need something to bolt it to. And normally, to be honest, the best way, if you're doing a steel frame, is to make sure your structural engineer gives you a rectangular hollow section. So a box section. Okay. And that's what we did here. The reason is, if you don't do that, and if you end up with a UB, so if you end up with a universal beam instead, there's nothing to fix to, and you end up having to get plates welded into the depth of that beam, which is just awkward. Much better to get a box. Okay. Now on this building, we were doing a slim floor construction, and what that meant was we had a steel plate welded to the underside of the box like that. We put a precast concrete plank in like this, and then we put a concrete infill topping onto it. So that was our floor build-up. Okay. Right. Just draw a few more bricks. Okay. Now we've got the same problem again, which is that any water dripping down the back of this brickwork will just get into here and will just find its way through. Okay, and the window's going in here in a moment. So we need to get rid of that. We'll just continue our lightweight steel frame inner skin as exactly the same as before. There's our CP board. Okay. Plasterboard skirting. So kind of same detail as at the ground really, but on an upper floor now. Now to get rid of this water out of here, same principle really. We need to take that water out of the cavity, and what you would typically do is, again, you would put a plastic cavity tray, so a sheet of flexible plastic, and that will take any water dribbling down that brickwork, and it will evacuate it through a weep hole again. So we put a weep hole in there. So any water, wow, it's snowing, dribbles down here, and it will drip out through the weep hole. Okay, you're not getting a lot of water in there, but a little bit. Right. Now, you may notice here and say, but you've got one brick that's not protected. So yeah, in theory, if any water got through that one brick, it's not getting evacuated by your weep hole, but in practice it doesn't really happen. Okay. So we've got that. What else do we need? We need our insulation. Like this. Okay. Normal cavity insulation. We need to tie this brickwork back again to our CP board, so we put in one of our cavity ties in here. Okay, and that deals with that, ties it back. We're going to stuff some insulation in here as well, because obviously there's lots of gaps here. I won't draw it for now, but you could stuff a whole load of insulation in these gaps. And then we need to get our window in. So down here we need our window. Right, let me just draw that. So we need lots of tolerance gaps to fit that window in. And the window is an aluminium curtain walling system. Okay, that. Double glazing. And that's got a cover cap on there. Okay, I've said it to a few of you this week in the 50-year the reviews of your work last year. When you come to something like a product, like a window, just find one on the internet and copy it. A lot of you are sort of making up windows and drawing things that don't look very convincing, but just Google and just find. I mean, I haven't drawn that well at all, but just find a product, because windows are products generally. There's our window, and it's kind of floating at the minute. And all they did with these windows is, if you imagine that is the vertical aluminium back box going down. That has a plate which comes out the middle of it, kind of like that, which has another aluminium plate that comes out. And the window installers just fabricated a small aluminium bent piece of metal here, which allowed them just to restrain the head of that window. Okay, because the window's sat down at the bottom, but it just stops it moving about. And interestingly, I've got some pictures to show you. The window is independent of the wall. So they actually installed the windows before the brickwork went in, which kind of feels odd. But you see, as I've drawn it, there's a gap there. They're not relying on that brickwork to fix the window. Okay? Then, just to tidy up the detail here, we had a small aluminium flashing in there, and a little bit of sealant. Okay, and that's pretty much the window head. It obviously all looks a bit messy inside here, and what we did there was we just had a sort of MDF. Let me just think, how did it work? Like that. Oh yeah, I remember now. We just had some MDF boxings made up to hide all of this, kind of like this, something like that, and that gave us a recess for our roller blinds. Okay, so that's just bits of MDF knocked up on site and painted, just to hide all of this sort of slightly messy bit and to nicely conceal the window blind. In the actual classrooms, we had exposed concrete because we wanted the thermal mass. Okay, but just to have a bit of MDF just to tidy up at the edge here, and then there would have been bits of timber in here. Okay. The thing with sort of joinery items like that, you can often leave that to the joiners. So you tell them what you want it to look like, but I wouldn't worry too much about telling them, which bits of wood to fix. They'll figure that out. Okay. So that is the detail. As I say, lots of insulation stuffed in here as well. Okay. And we stuffed insulation in there. Okay. Any questions on that before I move on to the eaves? Okay.
How do they fix the MDF on the ceiling?
The what, sorry? The MDF?
Yeah, they just grade on the...
They fix timber battens. So if they're fixing into steel work, they use a shot-fired fixing, a little explosive. So you walk on site and you hear, and you think you're not sure what's going on, but they've never let me use one. But and if they're fixing into concrete, they sometimes just drill it and use a plug or a bolt. Yeah.
It's not a really stupid question.
No.
But how just like, you know, in terms of like air tightness,
Yeah.
can air must get through past that when you get to flash it,
Here.
and then sort of like into that space and then into the building, like round the top of it?
Yeah, 'cause I haven't drawn it. I haven't finished the drawing, to be honest. You're dead right. You're dead right. As I've drawn it, yes. Let me finish it properly. What we've then got... Good question. Good point. We've got a membrane. It's quite fiddly, but it did work. In here. And this is stuck to the steel. And again, I mentioned it last week, it's this double-sided membrane, but it's not like double-sided sellotape, it's like really thick and sticky stuff. They just clean the steel off a bit, they can stick that to the steel, then they bring it round and they stick it to the aluminium window. Or sometimes they glaze it into the window system. Okay, it's quite fiddly, but they're very familiar with it. And it's an EPDM, so it's a kind of rubber. Okay, and now it looks, when you look at it, it sort of looks a little bit prone to failure. Okay, but the point is, on a building like this, we had to hit certain air tightness targets, and the contractor knew that, and all the subcontractors knew that. So there were a lot of workshops and there was a lot of work with the contractors to make sure that their work was to a good standard, because they knew if this building failed the air tightness test and we put a smoke pencil in and it was their window that was leaking, they were going to get into a lot of trouble. They were going to have to fix it, and it jeopardises their future contracts with the contractor. And in the end, our air tightness was fantastic, exceeded all expectations. But yeah, it's a very good point, Emma. Yeah. Okay. I'm going to very quickly try and do the junction at the roof. Right. Okay. Steel. I'll start drawing the steel first in this instance. There's our steel rectangular hollow section. And we've got our steel plate here with our concrete slab sat on that. Okay, and we've got brickwork. Okay. And on this building we had a parapet. I'm going to draw this a bit quick, okay, because we're running out of time. So a parapet is like a low wall around your roof. Now, under the CDM regulations, Construction Design Management regulations, there is an obligation on the architect or on the designer to try and design for safe maintenance, safe construction of a building. Okay? And under the CDM regulations, you must prioritise what they call collective protection. So in other words, a parapet will collectively protect anybody on that roof from falling off. A singular protection system is a man-safe system, a harness with a rope, with a lanyard and a system that can protect you. So, like it or not, CDM regulations are saying you should try and design parapets unless you can't. And it's a real serious issue. The point is that the CDM regulations become criminal acts. So if somebody falls off your roof, kills themselves, the judge says to you, okay, Mr. Architect, or Mrs. Architect, or Miss Architect, why did this operative fall off? And you say, well, I had a man safe. And the judge says, yes, but they fell off, and they were dangling in that man safe for an hour, and they got toxic shock syndrome, and they died because of that. So let me ask you again, why did you not have a parapet? Well, it didn't look very good. Okay. So the judge is not going to be terribly impressed with that answer. It didn't look very good. So it's quite a challenge for the architect here. If you think about it early on, you often find you can design a parapet in and it's absolutely fine. If you forget about it and you leave it to the end, then obviously it's too late to put a parapet on your amazing roof. So it's just one to bear in mind, because that is a real, it becomes a real kind of design consideration in practice. Okay, not so much in School of Architecture. Right, really quickly. We've got this parapet, and we're going to use our lightweight steel frame again, and we've actually got 2 layers of it. Okay, there's our CP board doing that. This down here would be just the repeat of the window detail that we drew a moment ago. Okay, so I won't draw that. This time we'll put CP board on both sides of the parapet. The parapet is very thick because we've got some steel posts inside it holding this thing up. Okay. So we've done that, and we need a roof. Now we've got a flat roof on this building. So what we've got is vapor barrier here. That vapor barrier, it's not to keep the rain out, it's to stop the moisture coming out of the concrete getting into your insulation. Then we'll have, in this case we used tapered insulation, and when you get out into practice, tapered insulation is great because it means all of your structure, all of your concrete can be flat. And that's much easier to draw. Yeah? Everyone will thank you for that. All your engineers, everything's flat. People hate it when it's like that, because everything's at a different level. Tapered insulation is great because you bring it to site and it has a fall on it and it all works. So there's our tapered insulation. And we continue that, we basically wrap that insulation all the way up the parapet so we don't get a cold bridge. Okay, like that. And the roof we used on this building is a hot melt called Derbigum. Derbigum, which is that. Okay. And it's a great product because you seal it together with some hot melted asphalt. It's very robust. If you puncture it with a nail, it will seal the hole. So in other words, it just doesn't leak. Okay. I think I've mentioned this before, but when you get into practice, you'll be pushed to try and use single-ply membranes like Sarnafil. But the trouble with the likes of Sarnafil is they leak. Okay, they typically get punctured on site. So before you've even handed over the building, somebody stood on a nail and punctured it. right? So if you can, try and get a Derbigum, a hot melt flat roofing system. It will just make life easier for everybody. It costs a bit more, but they just don't leak.
Is it hot when you put it on?
The sheets go down cold like that, but they join it with a hot melt, and they put a thin hot melt layer down to stick it down. Yeah.
Hot melts quite bad environment.
I don't think they're particularly any worse than the single ply membranes. I mean, you could argue that the benefit is that they don't need to replace them because they will have a 30 to a 50-year lifespan. I mean, this is for flat roofs. You know, if you can have a pitched roof, you're putting tiles or slates or whatever on it. Okay. Right. I'll leave it there because we've run out of time. But that was just the kind of principle. Okay. Any questions in the last minute?
One question. Can you go back to the photo of the windows?
Oh yeah, on here.
The other one you were telling me.
Okay, hang on. That one.
There's a line there.
Here?
Clear demarcation. Is it because the bricks were like a symbol in group and then put on the bracket?
Okay,
Or are they-
the vertical line.
yeah.
Yeah, this is a horizontal expansion joint. So brickwork will expand as it gets hot. So typically no more than sort of 10 meters you put an expansion joint horizontally. We put them on steel. So ours are at 7.2. You must also put a compression joint no more than every 3 stories apart. Okay. What I found is when I was younger, I'd get all hung up about them. Oh, I can't have expansion joints, they look terrible. We must get the foam that goes in it, it must be a perfect match. In reality, when you build it, you don't notice it. Okay. But yeah, good point. I'll just quickly show you very quickly some of the other images. So that's this is the windows in before the brickwork. That's the CP board, all taped up. Okay. What else is good? That's the stainless steel brackets looking down, holding up, well, they haven't put it on yet, but that will hold up the brickwork. This is in one of our wide cavities. That's a corner. So on a corner, they make a special corner piece for supporting the brickwork. Okay, that's the insulation, the Kingspan insulation.
Aidan,
Yeah.
at that stage, are you able to get other trades and to blow it?
The CP, yeah, the CP, once the CP board's in, it's pretty weather tight. Yeah. Which is great because, yeah, as you say, you get other trades in even before the brickwork comes in. Yeah.
This might be a stupid question, but if it's an RHS, how do you bolt into it?
Yes, it's a good question. They make a special bolt that has a sort of captive toggle device. So you push it in. Shall I draw? You push it through, shake it, and this bit in the bolt goes dong, and then you can pull it tight against the RHS. It's a good question. I had an engineer once telling me you never fix to it. To
what, sorry?
To a box. So if I go back to my drawing,
What, with the brick holder?
imagine you trying to fix something to that steel box section. You can't get your hand inside it to put a nut on. You get these special bolts that will do it with a toggle, so you don't need to get your hand inside. It's a good question. Yeah.
In relation to last week, with the timber constructions, was there a specific choice of using steel?
Yeah. I mean, it's a good question. We did a big audit on steel versus concrete. We were never going to get timber. Contractor was not this was a design and build. Contractor wouldn't go for timber. Big audit, environmental and cost. Concrete was the standout winner. But the contractor said, no, we're not doing it in concrete because there's only one concrete contractor in the UK at the moment who can do this scale job. And what they said is, imagine they turn around and say, oh, sorry, we're a bit busy. We'll be there in 3 months' time. And for a contractor, that is commercial suicide. So it's a shame. It would have been the better solution, but no. What we did achieve was we did get our exposed concrete soffits. And by using this slim floor, we did get our thin floors rather than doing a kind of conventional steel frame with the concrete sat on top. So, we were happy. We've got the environmental benefits of the thermal mass.